Autoencoders are highly efficient tools for data compression. They work by using an encoder network to squeeze high-dimensional data, like a detailed image, into a compact, low-dimensional bottleneck called a latent code. A decoder network then reads that code and attempts to reconstruct the original image exactly. But there is a severe architectural limitation if we want to use this to generate new data. A standard autoencoder maps each specific training input to a single arbitrary coordinate in the latent space. That leaves the vast distances between those specific coordinates entirely unstructured. If we pick a random coordinate out of one of these empty holes and pass it to the decoder, we get visual noise. The decoder was only trained on the exact coordinates of the training inputs. It cannot interpret the empty space in between. To reliably generate new, realistic data, our latent space cannot be a scattered collection of isolated points. It must be an organized, continuous manifold where the codes follow a known distribution we can easily sample from. Transforming that rigid, deterministic bottleneck into a smooth, probabilistic manifold is the specific mathematical challenge the variational autoencoder was built to solve. The VAE approaches generation through the lens of classical statistics. It defines an explicit probabilistic sequence. This diagram charts the process. First, draw a latent code, Z, from a simple, fixed prior distribution, usually a standard Gaussian. Second, pass that sampled code through a decoder network, defining a likelihood distribution over the data itself. But calculating the actual probability of any given data point requires an integral over every possible high-dimensional latent code. Because we use a nonlinear neural network decoder, this integral has no closed form. It simply cannot be computed. Since we cannot calculate this marginal likelihood, finding the exact posterior distribution, the reverse mapping needed to train the model, is mathematically impossible. We hit a wall. To scale that wall, we use variational inference. We bypass the intractable posterior by approximating it with a second neural network, the encoder. Because we cannot maximize the exact log likelihood of our data, the system optimizes a proxy objective instead. This is the evidence lower bound, or ELBO. This equation separates the objective into two distinct competing forces. The blue side is the reconstruction term. It rewards the model when a sampled latent code accurately decodes back to the original input. Left unchecked, perfect reconstruction wants to spread inputs far apart into highly distinct, confident codes, which recreates our original problem of empty holes. That is where the orange side steps in, the Kullback-Leibler, or KL divergence penalty. It aggressively penalizes the encoder for producing latent distributions that stray from the Gaussian prior, effectively squashing the separate codes together into a continuous, sampleable mass. For the standard Gaussian VAE, this KL term has a highly efficient, closed-form algebraic solution, meaning it adds zero computational overhead during training. Maximizing the ELBO is a delicate balancing act, simultaneously tightening the mathematical bound toward the true likelihood while forcing the latent space to stay organized. But there is a massive engineering obstacle preventing the ELBO from being trained. Computing that reconstruction term requires us to sample a random latent code. Look at this computational graph.
In deep learning, drawing a random number is a non-differentiable operation. Because there is no mathematical derivative for this, backpropagation hits a dead end. The gradient cannot flow backward to update the encoder. The solution is a mathematical sleight of hand called the reparameterization trick. It relocates the randomness entirely outside the network's core logic. Instead of drawing our code directly, we define it with this specific equation. We draw parameter-free noise, epsilon, from a standard normal distribution and inject it as an external input. Now watch the gradient. It bypasses the external random noise and flows smoothly through the deterministic pathways to the encoder. By expressing a random sample as a deterministic function of learned parameters plus external noise, the VAE becomes fully trainable via standard gradient descent end-to-end. This rigorous probabilistic grounding is powerful, but empirical results show a hallmark flaw. VAE-generated images are inherently soft, blurry, and lack high-frequency detail. This graph illustrates why. The network relies on a Gaussian likelihood and a squared error objective. When faced with multiple plausible sharp outputs, the squared error objective safely minimizes loss by predicting the mathematical average, and the average of several crisp, distinct possibilities is visually rendered as a blur. The second major failure mode is posterior collapse. A highly powerful decoder network learns to model the data distribution entirely on its own. Taking the path of least resistance, it drives the KL penalty to zero. The encoder outputs the pure prior, completely ignoring the latent bottleneck. Both failures trace to the ELBO's internal tension. Blurriness occurs when reconstruction loses to regularization, while collapse happens when the bottleneck loses to the decoder. Subsequent architectures manipulate the ELBO to solve these flaws. The beta VAE simply adds a multiplier to the KL divergence term. Increasing this regularization forces the network to isolate specific control variables, like separating lighting from rotation, but at the heavy cost of even blurrier reconstructions. The vector quantized VAE, or VQ-VAE, solves both posterior collapse and blurriness by abandoning continuous space entirely. By forcing the encoder's output to snap to the nearest coordinate in a rigid codebook, it breaks the smooth mathematical gradient. This physically prevents the network from sliding into posterior collapse. Once the data is encoded as a discrete sequence of tokens, it can be modeled exactly like language. By tokenizing the latent space, the VQ-VAE hands the heavy lifting of generation off to powerful autoregressive transformers, forming the basis of modern multimodal AI.
Pure continuous VAEs no longer hold the state-of-the-art for raw image fidelity, but their underlying mathematics were absorbed, not discarded. Today, the VAE serves as the essential compressor for larger systems. The latent in latent diffusion models is exactly this, a pre-trained VAE compressing high-dimensional pixel data into a highly organized, low-dimensional manifold. The iterative generation process occurs entirely within this compressed VAE space. Without the rigorous marriage of Bayesian inference and deep learning established by the ELBO and the reparameterization trick, the computational efficiency that allows modern AI to run on consumer hardware would be strictly impossible.